Hi gang. Today we're going to be talking about electron arrangement in atoms. And the first question you may ask yourself is, well, why would anybody even care about the electron arrangement in atoms? And to address that question, let's go back and think a little bit about human understanding of nature. One of the things that we've always been curious about is what exactly is our universe made of? And so one of the very first attempts to answer that question came up or resulted in one of the first models of the atom. And that model came about because of a question that this guy named Democritus asked. The story was that he was sitting on the beach and looking out at the ocean. And he was curious, and he thought, if I take that ocean and divide it in half, each half will still essentially be an ocean. But if I take each of those halves and divide them in half, and then smaller and smaller and smaller, will I eventually reach a piece of matter that is so small that it no longer retains the characteristics of an ocean? In other words, is there a limit to how small that I can divide matter? And Democritus thought that there ultimately was a limit. And so he said, if I take the ocean and divide it down small enough, eventually I'll reach the tiniest possible piece of matter. And so this blue circle is supposed to represent Democritus's tiny indivisible piece of matter. And Democritus called those tiny individual pieces of matter atoms. That's where the term that we still use today comes from. But it turns out that Democritus, his model, was not completely correct. Time goes by, and these guys named Thomson and Goldstein come along. And they have some new tools at their disposal that were not available before. They're able to take samples of material and expose them to very high voltages. And when they do that, they see that there are two beams that come flying off of the samples. And these two beams behave differently when exposed to magnetic fields. When they expose it to one magnetic field, one of the beams curves one direction, but the other beam curves the opposite direction. Well, they knew that charged particles will react to a magnetic field. And since these things were bending opposite directions, they said, well, those two beams that we're seeing must be charged particles, and they must have opposite charges. Therefore, the atom must actually be made up of these positive and negative charges. And since they knew that positive charges repel each other and negative charges repel each other, but opposite charges, positive and negative, attract each other, they just thought that all these positive charges must just be kind of mashed together, and they said that the atoms that Democritus had proposed really must be made of positive and negative particles, just kind of all mashed together, and they called that model the plum pudding model. Again, a little bit of time goes by, and another guy comes along, and he's got some other tools available to him that were not available before. He now has access to alpha particles. Alpha particles are very small charges, or very small particles of matter consisting of positive charges. And Rutherford says, well, if the atoms really are just like Thomson and Goldstein said, if they're really just arranged like in the plum pudding model, if I shoot these alpha particles into a sample of matter, they should just go blasting right straight on through without being affected, because the charge will all be distributed. But it turns out that's not what happened. When Rutherford shot his alpha particles through his samples, many of them came bouncing back. And he realized that the only way that could happen would be if those positive charges inside the atoms were all clustered together. So the plum pudding model was replaced, and they knew now that all the positive charges must be clustered together near the middle of the atoms, and the electrons then must be filling the empty space to the outside. And Rutherford proposed the idea that those electrons must be in orbit around that positive nucleus, very much in the same way that planets are in orbit around the sun. And so this is the beginning of the idea that, well, maybe it's the electrons that really control how things react. Since the electrons are on the outside part of the atom, those are the things that interact with other atoms and could be the mechanism for controlling chemical reactions. There was a problem, however. It turns out that if the electrons really did orbit just in the same way that the planets did, they should actually be able then to orbit at essentially any distance, because if they had any amount of energy, higher energy would orbit at higher levels, lower energy would orbit at lower levels, and they should have an infinite range that they could actually orbit. They should be able to orbit anywhere. Turns out they don't. They only orbit at very specific, distinct distances. So another model came along. This time it was proposed by Niels Bohr, and he said, well, Rutherford's model is close, but it's not quite right either. I think those electrons must exist only in distinct steps, distinct energy levels. And so Bohr's model was an improvement on Rutherford's, and it shows how the electrons are arranged and how they exist at very specific locations around the nucleus of the atom. So in our future videos, we're going to be talking about how exactly do we figure out where those electrons are, because it's where those electrons are in their positions around the nucleus of the atom that determine whether a substance will be a metal or a non-metal, an acid or a base, or any of the chemical properties that that substance will exist. So we'll look forward to seeing you again as we talk about those materials. See you later.